Hello everyone, this is group CS2333 Computer Science, Makerere University, and final year project. This is our project title, Micro Drone with a Proximity Alert System. Here are the group members of this project. Kawalabi Benjamin, Kauma Joel Joseph, Mwenza Sophia Sentam, and Watala Alexander Mark. This is the outline of our project presentation. We shall talk about the introduction, problem statement, related works, objectives, methodology, basically the system architecture, experimental and simulation results, conclusion, future research direction, and lastly, the references. Our introduction, the background of the drone. Small drones are not usually equipped with warning or evasion systems, and collisions can occur if flight input coordinates are entered incorrectly or if something enters their flight of path. There are dangers of collision with power lines, cell phone masts, especially with inexperienced operators. Due to airframe fragility, collisions pose a significant risk to small drones and warrant the need for training and acquiring expertise on flight path setting and manual maneuvering when needed. Yet, as drone operators would be community members who know the area very well, this is not expected to be a major issue after adequate training. Drones are widely being used in a number of fields, and their application ranges from filming, videography, agriculture, surveillance to robotics. Drones would have helped us in many sectors for example, agriculture, forestry to accomplish many activities, for example, getting the population species of trees in a forest and tracking sick animals on a farm, but their inability to detect unintended obstacles limits their operations due to collisions that result into damage. Next is our problem statement. The major issue associated with drones is collision with unintended obstacles within the air, which causes damage of unmanned aerial vehicle, UAVs. And it's also difficult to fly drones indoors successfully due to limited space, hence increased chances of crashing. The collisions of drones with electrical lines can lead to power outage and also security threats. Our next slide talks about our related works. Here we talk about LiDAR sensor for autonomous vehicle. Automotive radar and LiDAR sensors represent the key components of the next generation driver assistance functions. In contrast, LiDAR sensors show high sensitivity towards environmental changes. For example, dirt, snow, and fog. Rodaring's vision for its LiDAR technology is simple: to market it where it is sophisticated 3D and understanding or visualization of the environment is required. High definition LiDAR has its applications in robotics, map capturing, surveying, autonomous navigation, security, and automotive safety systems. Advanced driver systems ADAS, where LiDAR is a key solution, do not only provide a more comfortable driving experience, but also able to reduce the severity of accidents or even prevent crashes. Our objectives. Our main objective is to design and program a drone model that can detect unintended obstacles within the air and determine the proximity of the obstacles so as to avoid collision. Then our specific objectives of this project to design a drone with lead and buzzer indications per obstacle, to test the micro drone and the obstacle detection system, to implement a drone that can take off from tight places or indoors. Next is our methodology, and I'll call upon one of the members to take us through.
Hi everyone, I'm Benjamin. I'm going to talk about the methodology. For our research, well, we used observation and document review as our research methods. This is the system architecture that demonstrates some of the key components that are used in our project. The main drone consists of 4 drone motors with 4 propellers, with the Arduino Pro Mini controller, LiDAR sensor, lead and buzzer. The LiDAR sensor uses the IR for detecting any obstacles in front of it. It also, if any obstacle is detected, the LiDAR signals are decoded by the controller to operate a buzzer and LED for indicator of the obstacle proximity alert. The user is constantly alerted with the about of the proximity by modifying the LED and the buzzer frequency as per the proximity, so the drone can be controlled accordingly to provide collision. The small drone uses 4 motors to lift off and control the flight. The RC controller commands are interpreted and used by the flight controller through the RF receiver to achieve desired flight movement. The drone makes use of the Arduino Pro Mini to sense the proximity using LiDAR and operate the LED and buzzer accordingly. Moving on to the next slide, shows the data flow diagram that shows the processes that are involved in the micro drone. This is an explanation. This partial drone does not auto-avoid obstacles, just alerts the drone operator through an audio sound from the buzzer plus a LED indicator. In the diagram above, the user interface interacts with the drone control process, which receives user commands. The drone control process communicates with the drone and also sends drone status data back to the user interface. The object detection process receives data from the TF mini LiDAR sensor and provides object detection data to the user interface. The alert signal flows from the drone to the buzzer and the LED. The buzzer generates a sound signal which alerts the drone operator audibly, while the LED provides a visual indication. These components are connected in parallel with other processes, and the data flows in the system. This diagram demonstrates the algorithm that is used in to implement the obstacle detection. In this figure above, the LiDAR sensor scans the environment by sending pulses of infrared light to measure the distance of a possible obstacle. If no obstacle is detected, the drone continues to follow the current trajectory. Once an obstacle is detected, the LiDAR sensor signals are decoded by the flight controller to perform LED and buzzer indications to alert the drone operator to maneuver the obstacles and avoid collision, hence following the current trajectory. In case of a collision, a new trajectory is followed. With that being said, let me hand over the mic to the next.
Yeah, so good afternoon, everyone. Yeah, my name is Kauma Joel, so I'll be taking you through the next slide. So basically, our LiDAR sensor. Our LiDAR simulation is going to do with the LiDAR sensor. First of all, sending infrared lights to the object, and then they'll be bouncing back to the LiDAR so that it can capture the proximity. So it will be like so it will be able to capture the distance between the object and the LiDAR. So moving on. So basically, this is the explanation. In this case, Livox Avia was simulated. The solid-state LiDAR sensor manufactured by Livox Technology. It is mainly oriented to robotics, mapping, and position awareness applications. This LiDAR sensor is a time-of-flight device whose operating principle based on sending pulses of infrared light measure the distance in different directions. And this kind of LiDAR sensors typically have one or more light beams that can be directed, forming scanning patterns to obtain 3D point clouds for the sensor environment. So moving on, continuation, the system will alert the drone operator by intended obstacle, allowing for timely and safe navigation. The purposed solution offers potential benefits in various fields, including search and rescue operations. Inspector had to reach areas and exploration hazardous environments. So, yeah, so basically this is the diagram of this is the diagram of a microdrone. Yeah, basically it is, you are seeing the different components. Yeah, so moving on, I will invite the next colleague to take us through.
Good afternoon. I'm going to take you through the achievements we've been able to make in this project. The first one, detection of unintended obstacles within air and determine their proximity so as to avoid collision. So the time flight mini leader system provides the precise distance measurement capabilities, allowing the microdrone to accurately detect the distance between itself and the obstacle in its surrounding. The sensors range and accuracy were sufficient for obstacle detection both indoor and outdoor environments. Our second achievement is obstacle avoidance maneuvers. The obstacle detection system using the time flight leader sensor enables the microdrone to perform effective obstacle avoidance maneuvers. So this happens when an object is detected within a predefined distance by the sensor. The drone operator is alerted through an audio sound from the buzzer plus the LED indications. Therefore, in this project of ours, the drone doesn't auto avoid the obstacles. Then there is robust performance. The obstacle detection system demonstrated robust performance across various environmental conditions. It was able to detect obstacles accurately in different lighting conditions, including low lights and direct sunlight. The sensor's performance was also reliable in the presence of obstacles with varying surface properties and reflectivity. Hence, achieved detection of unintended obstacles within air. Then user experience and safety. The obstacle detection system enhanced the overall user experience and safety of the microdrone operation. It provided users with increased confidence and control over the drone's flight as potential collisions with obstacles were detected and avoided. The system's responsiveness and reliability contributed to a safer and more enjoyable flying experience. So those are the achievements we've been able to get in our project. The limitations and challenges we faced. The first one, the leader sensor's range was limited and the drone's effective obstacle detection and avoidance were constrained within a certain distance. The drone could only detect obstacles as close as 12 centimeters and as far as 12 meters. Additionally, the sensor's performance proved to be affected by a diverse weather conditions, such as heavy rain, reducing effectiveness in such situations. The second one is limited battery life. The microdrone wasn't in position to perform all its functionalities fully due to the existence of a weak battery. This affected the reflex functionalities of the drone as it encounters an obstacle. At some point, the buzzer and the LED could give feedback to the drone operator in form of audio sound and LED indications such that it changes its flight path manually and guide the drone over the obstacles. So the above are the limitations and challenges. In conclusion, the overall implementation of the obstacle detection system using the time flight mini leader sensor on the microdrone demonstrated successful obstacle detection and avoidance capabilities. It showcased the potential of enhancing microdrone safety maneuverability, and usability in various applications and such surveillance. Thank you for watching us. That's all we had.